Have you ever wondered about the hidden forces shaping the universe? While black holes and dark matter often steal the spotlight, there's another cosmic mystery that has puzzled astronomers for decades, a powerful force pulling galaxies toward the edge of the universe. What is this enigmatic phenomenon, and how does it shape the very fabric of our cosmos? Stay tuned as we dive into the mind-bending mystery of the Great Attractor. Imagine this. Thousands of years ago, small tribes of humans gathered around the dim glow of a campfire, staring into the pitch-black night, wondering what might be lurking just out of sight. Fast forward to today, and in many ways, not much has changed. Our campfires are brighter, illuminating entire planets and reaching far beyond Earth into the vast stretches of space. Tools like the James Webb Space Telescope now let us peer to the very edge of the observable universe. But no matter how advanced our technology becomes, there's always a boundary, a place where light fades and the unknown begins. Beyond that edge, the observable universe remains a mystery, shrouded in darkness. Why? Because this boundary marks a limit we can't cross. It's where space is expanding so fast that not even light can bridge the gap. Nothing from beyond this edge can ever reach us, and we can't reach it. Unlike the campfire shadows of old, this darkness isn't something we'll ever conquer, or so we thought. Then came 2008. Scientists analyzed hundreds of galaxy clusters and found something baffling. They were moving fast, all drifting toward one specific point at the edge of the observable universe, far faster than any known force could explain. It was as if something beyond that edge was pulling them, or perhaps had pulled them long ago, stretching its influence across billions of light years. Something unimaginably massive might be hiding out there, just beyond the final dark. This mysterious motion of galaxy clusters even earned itself a name: dark flow. What is it? What's driving this mysterious phenomenon? And what could it mean for our understanding of the universe? Hi, I'm Alex McColgan, and welcome to Astrum. Today, we're diving into the enigma of dark flow, a controversial discovery that shakes up our models of the universe's origins. Let's start with the basics. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP, to map the cosmic microwave background radiation, the faint, ancient glow left behind by the Big Bang that blankets the universe. By 2010, WMAP had completed its groundbreaking mission, though data releases began well before that. These insights were revolutionary, answering questions like how flat is the universe? And what makes up the cosmos? Matter, or dark energy? Among the scientists eagerly analyzing this data was Alexander Kashlinsky. Leading a team at NASA's Goddard Space Flight Center, Kashlinsky wanted to compare the cosmic microwave background map to the motion of galaxy clusters. He was looking for patterns, hidden connections in the way galaxies were moving through space. But this wasn't easy. The challenge required precision and creativity. Kashlinsky's team tapped into a unique tool. The answer lay in a phenomenon known as the kinematic Sunyaev-Zeldovich (KSZ) effect, a faint but measurable clue hidden in the cosmic microwave background, CMB. Here's how it works. When the CMB passes through a galaxy cluster packed with energy, it picks up just a tiny bit of that energy. This can happen in two ways. If the cluster is extremely hot, it heats up the cooler CMB radiation. Or, if the cluster is moving quickly, it transfers some of its kinetic energy to the radiation. Either way, the CMB gets a slight energy boost. By analyzing this effect, scientists can infer the existence and motion of galaxy clusters. But here's the catch. This boost is incredibly small, practically microscopic. To detect it, Kashlinsky's team had to use data from over 1,000 galaxy clusters and apply advanced statistical techniques to tease out any patterns. And they found something astonishing. There was a massive flow of galaxy clusters, stretching across 2.5 billion light-years. These clusters were moving at breakneck speeds, between 600 and 1,000 kilometers per second in the direction of the Centaurus and Hydra constellations. The real mystery? There's nothing we can see in that direction that could explain this motion. No visible structures or known forces could account for such a massive gravitational pull. This led to a mind-bending implication. Some colossal source of gravity, something we can't see, must exist at or beyond the observable edge of the universe. A mysterious, unseen force shaping the cosmos from the shadows. And this idea is incredibly controversial. But before we dive deeper, let's first ask, is it even possible for something beyond the edge of the universe to influence us gravitationally? At first glance, you might think the answer is no. After all, as I mentioned earlier in the video, nothing beyond the observable universe can affect us anymore, and we can't impact anything out there. This is a result of space expanding so rapidly that it outpaces the speed of light. When that happens, we lose the ability to interact with anything beyond that boundary, even gravitationally. I go into more detail on this in my video about the end of the universe. But here's the twist. There's a loophole, and it has to do with a time period early in the Big Bang known as cosmic inflation. For those unfamiliar, back in the 1970s, scientists were puzzled by a strange observation. No matter where you look in the universe, large sections of it seem eerily uniform, same temperature, same distribution of mass across vast distances, even regions that had never interacted with each other. For example, the edges of the universe on either side look strikingly similar, even though they've never been able to meet due to the vastness of space. This is called the horizon problem. That's when American physicist Alan Guth had a groundbreaking insight. He realized that the answers to these strange uniformities might lie in the very beginning of the universe. In the early universe, everything did interact with each other, kind of like when you mix blue and red dye in water, and after enough shaking, they blend into a uniform color. But for this to happen, and for everything in the universe to spread out the way it has, there needed to be an incredibly fast expansion of space at the very beginning, on top of the already rapid expansion from the Big Bang itself. Now, this is where things get mind-blowing. Physicists believe this super expansion occurred just after the Big Bang and lasted an insanely short time, about 1033 seconds. Yes, that's 1/1,000,000,000 of a second. But during that brief moment, space expanded by a factor of 1026, meaning it grew 1026 times bigger in the blink of an eye. To put that in perspective, it's like going from the size of a bacterium to the size of the Milky Way galaxy in less than the time it takes to blink. So why does this matter? Well, this rapid expansion is what makes the Big Bang model work. It explains how distant parts of the universe, now separated by unimaginable distances, were once close enough to interact and mix. It allows for the uniformity we see across the cosmos, even in regions that are now unreachable from one another. There are even some respected theories on how this expansion happened, involving complex concepts like scalar fields and the false vacuum state, but that's a lot of heavy physics. For now, just remember this key point. Dark flow might make sense if, during this brief pre-inflationary period before atoms even formed, there was. One possible explanation for dark flow is that our part of the universe got tugged toward a particularly dense section of the cosmos, a region with an enormous amount of gravity. This massive pull could have occurred during the period of cosmic inflation, which rapidly expanded space and pushed this gravitational source far beyond our observable universe. But the key idea is this: once something is set in motion, it tends to stay in motion. So, the galaxy clusters that were once pulled toward this unseen mass are still drifting in that direction, continuing with the cosmic flow. But, as I mentioned earlier, this idea is highly controversial for two major reasons. First, dark flow requires an enormous concentration of mass, just outside our universe, for it to make sense. This would mean there are far more stars and galaxies out there, packed into a much denser region than our current models predict. and that directly challenges the whole reason Alan Guth proposed cosmic inflation in the first place: uniformity. The universe we observe is largely uniform, meaning mass is spread out relatively evenly, no matter where you look. Moreover, the universe is isotropic, which means if you measure the movement of everything in the galaxy, all the velocities should cancel each other out. Dark flow disrupts this uniformity. It suggests that just beyond the edge of the observable universe, things are not as uniform as we once thought. There's still this immense, hidden mass out there, but it's beyond our sight. And that's a bold, controversial idea, one that challenges the very foundations of how we understand the universe. Dark flow raises a whole lot of questions. If the universe isn't actually uniform beyond our horizon, does that mean we just got cosmically lucky to find ourselves in such a perfectly flat patch? What does this mean for our theories about the universe's formation and cosmic inflation? After all, inflation was supposed to explain why the universe is so homogenized. But if it's not, what does that tell us about the very foundations of inflation itself? But here's the kicker. The second reason dark flow is so controversial is that it might not even exist at all. While Kashlinsky's team at NASA is convinced of dark flow's presence, the European Space Agency's ESA Planck team took a deeper look using their own high-resolution map of the cosmic microwave background, CMB. The Planck probe, which launched in 2009, 8 years after Double, UMAP, analyzed over 1,000 galaxy clusters and found no evidence of dark flow. However, Kashlinsky and his team weren't ready to give up. They reviewed the Planck data themselves and argue that they can still see signs of dark flow. So, the debate is far from settled. In fact, Kashlinsky's team announced they'd be conducting an even more detailed analysis, combining both Planck and Double UMAP data to seek stronger evidence. But as of now, the results are still pending. Until we have more concrete proof, it makes sense to assume that dark flow might not be real, that there's no mysterious force pulling galaxies towards some unseen mass just beyond our vision. But then again, as with any great unknown, it does leave us wondering. Science doesn't care about what's convenient. The truth is the truth, and it's only a matter of time before we uncover it. One day, perhaps, we'll finally have an answer to what lies beyond the visible universe and whether dark flow is real. But even if we do find that answer, all it will do is push the darkness back a little further, revealing yet another cosmic boundary that will leave us wondering once more. There will always be more to discover, more to understand. Humanity's insatiable thirst for knowledge and exploration will never stop. The idea of traveling to distant stars is awe-inspiring, and I truly hope that one day we can make that dream a reality. But I can't help but wonder, while the beauty of space will surely take our breath away, will it also bring us some of the same stresses we experience here on Earth? I recently took a trip to Croatia, and while the country itself is stunning, I quickly realized how much I rely on having internet on my phone. When you're navigating an unfamiliar place and suddenly start worrying that your data plan is running out, it can be pretty stressful. I should have used a sponsor of today's video, SimSimi, which would have made everything so much easier. SimSimi is perfect for frequent travelers. It's an SM app that you only need to download once. Then, whenever you're headed to a new country, just select your destination and a plan, and you'll have internet access on your phone as soon as you arrive. No more hunting for local SIM cards, no more hopping between Wi-Fi spots, and it's actually cheaper than roaming. Now that's one less thing to worry about on your travels. SimSimi reduces, or even eliminates, roaming charges in over 160 countries, and the app works on both iOS and Android devices. So, why not give yourself some peace of mind the next time you're traveling abroad? Just scan my QR code or click the link in the description below to visit simsimi.com. When you use my link and the code ASTROM at checkout, you'll get a 15% discount on eSIM data plans. It's a game changer. Thanks for watching. We're now getting very close to our goal of 1,000 astronauts on Patreon, and I can't thank you enough for answering the call. The closer we get, the more we are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blisovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blisovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.